All right, so the derivative of a function, like we just said, is very similar formula. In fact, the same formula we were using for tangent to a line and rate of change when h is approaching 0. The only difference is they've now changed our symbols for a lot of this stuff. We call this f prime. Okay, so this uppercase 1 here is our f prime. So we're looking at the derivative of f at a. And this can be written several different ways. We can write it as y prime. We can write it as the derivative of x in respect to y. This is very similar to the change in y over the change in x. Okay, we're probably going to focus most on our function notation in terms of writing this. Okay, but realize when in the book they can write it many different ways. I want you guys to just quickly look over those definitions at the beginning of this lesson, just so you guys realize that this can be written in 3-4 different ways. Okay, either of these are fine. This is our first principle. Okay, and as we go later into this chapter, we're going to find out shortcuts instead of plugging things into first principle. The good thing about this is we've worked with this formula in chapter 1. Okay, when finding tangent of line or rates of change. So what we're going to do now is we're going to show how we can apply this. And instead of finding at a specific point, we're going to turn it into an equation. So we're going to skip example 1. We're going to jump right to example 2 in your textbook. Okay. And instead of finding to a specific point, this is going to be finding the derivative of an arbitrary value. Okay. So deriving an arbitrary value. So the second example says determine the derivative of f at x. So we're going to find f prime of x squared to an arbitrary value of x. All right, at just x. So normally they write in at x equal to maybe 2, okay, or maybe x equal to 3 or -8, something like that. We're going to find it to an arbitrary value of x because part B of this question we might as well include it. Part B is going to ask us to determine the slopes of the tangents at x when x is equal to -2, 0, and 1. So instead of putting it into our first principle formula 3 different times, it is showing us a faster way of doing it. Of finding the first principle of just the arbitrary value of x and then using that equation to find all these slopes at the end. So we'll go through this process. We know our formula. We're going to find f prime, which is the limit of h as it approaches 0, f plus x plus h minus f at x over h. And if you notice, this is the exact same thing as our formula on the previous page. The only difference here, I can't quite show it, is they've used a plus h, and we've plugged in the arbitrary value for the a value. So it's x plus h. Okay, so let's go back to this page. We're going to now expand and simplify when putting in this function. So our limit as h approaches 0 again. Remember, our function was x squared. Okay, so our first part is going to become x plus h squared minus x squared divided by h. We're going to expand and simplify that bracket. So we're left with limit of h as it approaches 0, x squared plus 2xh or 2hx plus h squared minus x squared divided by h. So it's looking a little like a proof, but important to know how to do this. If you guys notice, we have x squared, or positive x squared and negative x squared. They're going to create a 0 or cancel out. So we're going to be left with the limit of h as it approaches 0 at 2hx plus h squared divided by h. And remember, usually when we're in our first principle here, we're trying to eliminate the h on the bottom of the fraction. And the reason for this, if you guys recall, is because we're looking for when h approaches 0. Well, if 0 is at the bottom of the fraction, we have an undetermined value. we won't be able to solve it. So we need to get something else on the bottom of this. We're going to factor the h out on top. Whoops. Limit of h as it approaches 0. We get h 2x plus h divided by our h value. I'm sure many of you have already jumped ahead. We can cancel out or create a 1 with these h's here. So we're now left with the limit of h as it approaches 0 with 2x plus h. This is where we're going to take our value of 0, because when h is approaching 0, it's infinitely close to it, so we just take it to assume the value. H is going to essentially be 0 in this case, so our limit is going to be 2x, okay? Or sorry, in this case, our slope. So what we just found there is the slope at any point on x. So now that we have this equation, we can go back up to part B. And part B said find the slopes of the tangent when x is -2, 0, and 1. So I'm going to jump back to the bottom again. Part B, they want it when x was equal to -2, 0, and 1. Well, instead of plugging those values into the first principle formula and carrying out this process 3 different times, now that we've actually got an equation at the end here, our 2x, we're just going to plug them in at the end here. So when x is -2, our slope is going to be -4. We plugged it into the 2x, okay? When x is 0, our slope will be 0. And when x is 1, our slope will be the number 2. We've just plugged it into this formula of 2x, okay? So our slopes are -4, 0, and 2.